Hello, this is my presentation for Lab 5 Magnetic Braking with Faraday for Physics 2212. The purpose of this lab was to collect observational data from a magnet falling through a conductive tube of aluminum foil, model the magnet/tube interaction computationally, and compare the computational predictions to the data. Some of the physics concepts used within this lab were the Biot-Savart law, Faraday's law, Newton's third law, and magnetic dipoles. A preview of the results were that the experimental time average was 0.488 seconds, while the computational time was 0.28 seconds. Some assumptions of our model is that the bar magnet acts as an accurate depiction of magnetic dipoles, with north being positive and south being negative. The magnetic moment of the magnet is the same as experiment 3, and the air resistance is negligible. For this experiment, we took a tube of aluminum foil and dropped a bar magnet through it in order to determine how conductors affect the time it takes for a magnetic dipole to traverse through them. We physically gathered our data through recording ourselves dropping the magnet through the tube and subtracting the time it takes from the entrance of the tube to the exit. Repeating this process 5 times, we got the average time to be 0.488 seconds in flight. The measurements of the tube itself are shown on screen. Moving on to the computational portion of this experiment, we see this is my GlowScript link. We first begin by creating the tube itself in order to be as close as accurate as we can to the simulation. In order to simulate this experiment, we modeled the tube of aluminum foil as rings perpendicular to the y-axis. From Lab 3, we were able to use information such as the magnitude of the magnetic dipole moment and a function to calculate the magnetic field of the bar magnet as it moves through the tube. The code screenshot shown on screen is what we used to determine the magnetic flux as the magnet fell through each ring of the tube. The left screenshot displays the simulated magnet falling through the tube, where we can see the north end of the magnet with the red coloring and the south side of the magnet with the blue coloring, displaying the theoretical rings of the tube that are affected as fall time of the magnet increases. As the magnet traverses through the tube, the velocity increases and acts in opposition to gravity. Based on our simulation, the magnet would take just under 0.30 seconds to complete its trip. For our first discussion question, what if the resistivity of the conductor reduced as close to possible zero? How would the dynamics of the falling magnet change? The induced current would increase, leading to an increase in magnetic force. This works in opposition to gravity on the magnet, which is the downward force acting on our object, while the magnetic force is increasing in an upwards direction. This all in turn increases the time it would take for the magnet to travel through the tube. What if holes or slots were cut into the tube? How would this affect the ring currents in our model? If there are holes, there would be less rings, therefore our induced current would decrease, allowing the magnet to travel with less resistivity, causing time of travel to be shorter. Some possible sources of error would include the miscalculation of the magnetic moment in Lab 3, the negligence of air resistance, the mismeasuring of dimensions of the tube in the real-life experiment, or not having a significant enough amount of foil on the tube to make a noticeable difference in time of flight compared to no foil. When calculating the percent error compared to our actual measurements to the simulation measurements, we get a 43% error, which is indicative that one or more of these error sources is applicable. Thank you.